We're going to talk about some basics of solar installation, some terminology that needs to be understood before creating arrays and loading things up, configuring your solar system. Really, it's just to get familiar with this terminology. Honestly, I'm going to use this as a cheat sheet to go back to when we actually do the installation. So I figured I would make a video and share the wealth of knowledge. Again, I'm not an expert. I just did a ton of research and really honed in on the things that I care about that are important for our particular situation here. I'm focusing primarily on residential solar. I'm not doing small RV solar installation. We're trying to get to net zero at our house. So that's the focus of all of my videos. So to jump in, the two primary circuits, and now basically circuit is just a way to arrange different devices in the context of solar. It's a way to arrange different panels or charge controllers, different devices, different objects that either emit, transmit, or change electricity. So there are two primary ways. You can either link things in parallel or link things in series. And depending on what you do, it has an impact on voltage and current. Again, current or amperage is how much electricity could pass through something. Voltage is the force that electricity is traveling through. So in parallel connection, this is the example of a parallel connection. What happens is you have your positives and negatives all being connected together in parallel and then coming together to a single area, right? When you put solar panels in parallel, what happens is you increase, or the voltage stays the same, but you increase the current. So how you basically increase your pipeline, but you keep the force of that electricity the same. So in this example, when we put 3 solar panels in parallel, and again, all the positives are connected together and all the negatives are connected together, and they come together at a single spot. I stole this picture from Wikipedia. I'm just trying to simplify it, and it serves my example. So a parallel connection, all your positives are connected together, all your negatives are connected together. It's a lot more wiring. The good part of this is you keep voltage the same and the current actually gets increased. In a serial connection, you basically daisy chain the positives and the negatives. So the positive from here is connected to the negative from the next panel, and the positive from here is connected to the negative in the next panel, and then you basically have a positive coming out of here and a negative coming out of here, or the other way around. And you could see in this example, you're using a lot less wiring than this example. There's positives and negatives to both sides. When you put it in a serial connect circuit, voltage adds up, but the current stays the same. So voltage, again, it's the force of electricity, and current is how much electricity it can actually carry. The pros of doing a serial circuit is that you can use a lot less wires. Specifically, when you talk about solar panels, what happens when this middle part, like there's shading, right, where you don't get sunlight through, electricity can't travel through it. So the downside of it is you slow down your whole system. And again, your voltage is a lot higher. In a parallel connection, you do use a lot of wires, but if for some reason, let's just say there's shading on this middle part, you still get electricity through the top panel and the bottom panel. You don't need to worry about one part of your solar panel getting shaded. And there's other benefits, and I'll go into those deeper when we actually get into the installation of our solar panels. But for the purposes of this conversation, the purpose of this video that I'm making, all I really want you guys to walk away from here is the difference between a parallel and a series connection circuit. Parallel, all the positives come together and the negatives come together and they join at a single point. In a serial circuit, the positives are daisy chained with the negatives, and you get just a lot fewer wiring. You get one positive coming out of here and one negative coming out of here. And that's how the circuit's built. So the next topic is charge controller. So the way charge controllers work, and And I'm talking about charge controllers separately than like the inverters. I know nowadays they have those single units where everything is together, but what I found is that if you separate them out, it's easier, it's much more modular and easier to expand. Where if you have your charge controller and your inverter all in one box, when that box goes, your solar productivity is just down the tubes. But if you can separate them out, if you have failure in one part of your system, the impact of your blast radius is much smaller. And so the way you size a charge controller is you take the total number of array wattage divided by the voltage of your battery bank, then multiply by 1.25. So this 1.25 is just for security. So just thinking about it for a second, you're taking the reason why you're doing this, the reason why this calculation is there, your total wattage of solar panels. So regardless of if you're putting it in parallel or serial, your wattage determines how much electricity you're taking from the solar panels and you're going to shove into the batteries, right? So the voltage is basically the force that the batteries can take electricity. So if you think of the wattage is wattage, the calculation for that is voltage times amperage. So the force of electricity times how big of a tunnel you get wattage. So what you're saying when you're sizing your charge controller is all this electricity I'm generating, how quickly can I put it into the battery, right? And your battery has a limited capacity depending on the chemistry of that battery. It could be 12 volts, 24 volts, 48 volts. Now they have 96 volt batteries. It affects the life of the battery, right? Like if you shove 48 volts down a 12 volt battery, you're going to burn the battery. Like the battery's chemistry can't handle that. So because of that, you need to be really careful. And why sizing a charge controller is so important, you need to be careful how much electricity you're putting into it. And again, even this 1.25 is a safety net that even if you put more electricity, you're not going to destroy the batteries or burn your house down. So in my case, I have my array will generate 5,500 watts of electricity. My first array that I'm setting up will be 5,500 watts of electricity. My battery bank is a 48 volt battery bank, right? I have a total of 20 kilowatts that my batteries can handle, but in terms of voltage, it's just 48. So 5,500 divided by 48 times 1.25 gives me 143 amps. So my charge controller needs 143 amps. What I decided to do was break up. They do make 150 amp charge controllers as well as 200 amp charge controllers. Like you could have sized it to add more. But what I decided to do is to get smaller charge controllers and then connect them in parallel. So that would increase, if we go back to our definition, it would increase our amperage, right? So if I get an 80 watt charge controller, if I get two 80 watt charge controllers, put them in parallel, they could handle 160 amps. That should be more than enough power for what my batteries can handle. And again, I'm doing that to minimize my blast radius. So because I'm doing a residential solar installation, I'm trying to make these pieces as modular as possible so that if one charge controller goes down, I'm not completely dead in the water. I'm still charging my batteries with the other set. And then I could go get another charge controller and add it onto my system. One of the restrictions that I'm placing on this solar installation that I'm doing is making sure I can handle all of different things that could go wrong. I want to make sure the system is modular enough that I could, take one piece out, plug in another system as the battery banks get better and increase in quality. I do want to swap them out eventually. I mean, a long time, hopefully, because it's a huge investment. But I don't want to be tied down to a single system. So I wanted to make sure it's modular enough to handle different scenarios. And then our next topic is how to size the battery bank. Basically, the math that's used for battery banks is kilowatts used over time. So let's just say my air conditioning unit uses 1 kilowatt of power per hour, right? If I run my air conditioning for 10 hours, I need 10 kilowatts in a day. So 1 day's power that I need to cover in my battery bank is 10 kilowatts. If I had no sun coming on and I want to run my air conditioning for 1 full day without worrying about anything, I need at least 10 kilowatts just for my battery bank. So the calculation for how to size a battery bank really depends on your usage. What I did at my house is I got a sense monitor and I plugged it into my circuit breaker just to see what my flow of electricity is throughout the day. The sense monitor gives you a lot of, and there's other devices that do this. I measured my total usage at my house. I didn't go for the individual, like, how many computers do I have? How many refrigerators and toaster ovens and microwaves? I just wanted to see blanket across my whole circuit breaker, how much electricity am I using and what do I need to generate to sustain my house for a day. I didn't go into multiple days just to sustain my house in a day. And what I settled on is I don't have it here, but what I settled on is a 5,500 kilowatt solar array that's charging 20 kilowatts of battery. Now, again, if I lose sunlight for a day, I'm out, right? But I didn't want to spend a ton of money to build out a full system. I'm trying to do this in small pieces, make sure I install stuff, I test it out, make sure it's working, and then increase to my next step. I don't want to do everything all at once. I want to just do it piece by piece and make sure the system's modular enough so that I can increase the different pieces of it over time. So for the way I size my batteries is I need 20 kilowatts of power, assuming that my solar panel array was 5,500 kilowatts that it could generate for 1 day's worth of power. And then depending on how that goes, I'll size up over time. And then how to size an inverter. I did another video that talks about low frequency, the benefits of low frequency and high frequency. But again, inverter really depends on what you want to do with your application. Since I'm doing residential solar, I want to make sure I get an inverter that can handle the full load that my house needs to generate. And in my particular case, my inverter needed to generate between 8,000 kilowatts to 15,000 kilowatts at any given time. It's a lot, but I have a ton of people living here that is using a lot of electricity. But at any given time, the maximum I've ever saw in my sense monitoring, the wattage go up was 15,000 or 12,000. So I sized it a little bit higher. And the lowest it went down to like 500 watts in the evening time. So I needed an inverter that could handle all that. And what I settled on is a low frequency split phase 48 volt inverter by PowerJack. I don't know how good it's going to be. You guys are going to find out the same time I do. So those are just some basic items that I want to cover. Inverter, battery bank, charge controller, which is basically and then solar array wiring. 4 basic components of a solar system that you would install. I mean, not just residential, but anywhere. You need panels to generate electricity, or you need turbines or whatever. You need a charge controller to charge your batteries. You need a battery bank, and you need an inverter. I just wanted to do this video to go over terminology, so I'm not explaining myself every video, and we could speak the same language. Hopefully you found that useful. I'll check in with you guys later.